All right, last thing for today, we're going to do what we call two sample z-tests. So these are, again, just a different type of hypothesis tests. So we've done testing when we have large samples. We've done testing when we have small samples. And then this is testing when we have two samples and comparing two samples to each other. And so that's what we're going to look at today. The process, again, similar, just a little bit of a twist to it. So a good way to think about this, so the question is do you see billboards? So if a billboard company, and hopefully this will understand, I hope you guys understand what we mean by two sample tests. So a billboard company takes a simple random sample of 500 Salt Lake City residents and find that only 26 know that Calvin Coolidge was the 30th president. Then they put up several yellow billboards that say Calvin Coolidge was the 30th president. After a few weeks, they take an independent, simple random sample of 500 residents, and 158 answer correctly. And the question is this evidence that shows that people see billboards? And so this example of two samples because they sample before the billboards and after the billboards. And the nice thing about this is these are two independent, different samples. It's like they sample them and then they throw everybody back in and sample. They might have actually gotten some overlap of people, but because they're simple random samples, then that's what we're looking at. So we want to know if this is evidence. So we've got sample 1 and sample 2. So again, the process is going to be very similar. We're gonna want to write our hypothesis, then we're going to want to find our test statistic, and then find our p-value. And then make a conclusion based on that p-value. Okay. So before I write my hypothesis, it would help if I know the percentage, the observed percentage. So we're just going to find that. We know that 26 out of 500, so we're just going to go 26 divided by 500 for this one. And when we do that, and if you times it by 100%, times by 100%. That's going to give us 5.2%. And then the second one, we know 150, the second sample after the billboards, 158 out of 500. And times by 100. And so when we do that, we're going to get 31.6%. So you can see there's a difference, and that's what we're looking at. We want to know, did it make a difference, or was it just due to chance? Okay, so same steps. We're going to write our hypothesis to start with. So start with your null hypothesis. Our null hypothesis, and when we're doing two sample tests, we just want to know, is there a difference? So our hypothesis is just going to state that the billboards have no effect, or no effect. It means that the difference in our observed percentage is just due to chance, is what that's saying. And so our alternative would just state that the billboards, again, you want to write this down every time. The billboards do have an effect. Okay, so that's step number 1. Step number 2 is to find our test statistic. The only problem with this is when you're actually looking at two different samples, we could have two different ones. So what we're going to use is what we call the expected difference. So this is like our EVD diff. So this is our expected difference. And then we're going to find our observed difference. So we're just going to find the difference. Our expected difference correlates with our null hypothesis, says that there's no effect. So our expected difference is just going to be, there's a 0% difference in our expected difference because we expect there to be no difference. Our observed difference, we're just going to take our observed percentages, the 31.6 and the 5.2. We're going to subtract them. And I'd suggest just doing the big by the small just to keep it positive. So 31.6 minus 5.2. And that's going to give us 26.4%. That's our observed difference. Okay, so this is going to help us find our test statistic. The other thing we need is our standard error. And so when we have two things, we need a standard error difference. The way to find this is to use this nice little formula. Just take the square root of a squared plus b squared. So a is the standard error of the first, and b is the standard error of the second. So there's a little bit of work here for this one. We've got to do a little bit of work for this one. So let's look at this. So first one, this again, first one we had what, 5.2%, and the second one we had like 31 point, what was it, 6, I think. Yep. And so again, we're just trying to find our standard error here for this so that we can find our test statistic. So our standard deviation here of the box, we need to be able to find our standard deviation of the box. And if you remember, to find standard deviation of the box for a percentage, we have to take the square root of, remember, 1s times 0s, the percentage. So this is going to be 0.052 times, if we could take 100 minus 5.2, that would give us 94.8, so we'd go 0.948. Okay? This is how you find your standard deviation of that box. We've done this, same idea here. This gives us 0.22, and then from there we can find our standard error for the percentage of just the first sample. And so we're going to go 0.22. Remember our standard deviation divided by the square root of our draws. Well, we sampled 500 people. And when we do that, we get 0.98. Okay. So yeah, we get 0.98. Sorry, I forgot to write this down there. Remember, we got to times this by 100. That's what that gives you. Okay, we've got to do that same thing. We've got to find a standard error for the second sample. So we're going to go to the square root of 0.316 from our observed percentage. Then we're going to times that by 100 minus 31.6. And when we do that, we get 68.4, which is going to be 0.684. And we're going to compute that. And when we do that, we're going to get 0.46. It's my standard deviation of my box. Hopefully everybody's good with that. Remember, we're just taking the observed percentage as a decimal times by 100 minus the observed for that. Again, this should look familiar. And then our standard error percentage, we're going to take our standard deviation of the box, so 0.46, and we're going to divide that by square root of our draws, which was 500, again times by 100%, and that gives us 2.06. Okay, and this is all so that we can get our standard error diff, or difference of our standard errors, because everything has to be equal. We've just found our expected difference and our observed difference. We have to have a standard error difference as well. So let's do this. Let's just do this right down here, our standard error difference. Again, we're going to use that formula that was on the previous slide right here. Square root of a squared plus b squared. Remember, a is the standard error for the first, and b is the standard error for the second. So we're going to go square root of 0.98 squared plus 2.06 squared. And when you do that, you're going to get 2.28. So that's our standard error difference. Now, the reason why this is just a longer process, it's the same, it just, you feel like you should be done at this point in time, but we still, remember, we're still trying to find our test statistic. So we need our observed difference minus our expected value difference divided by our standard error difference. Okay? So remember these two numbers here, we had 26.4 and 0. And then we found 2.28 as well. Okay, so again, we're going to go 26.4. That was our observed minus our expected is 0. All over 2.28. That's our standard error difference. And when we do that, we're going to get 11.58. That is our z-score. It's 11.5 standard deviations away from normal. So hopefully you guys would notice this is going to be, our p-value is going to look funny because remember we standardize over 0. 11's like way in the heck out here. And so we're trying to find everything to the right of that. And so we're going to get a very, very small one. But you can do it in your calculator if you want. Again, we'll use normal CDF for this. Don't use the TCDF. We only use that for small ones. We'll go our left bound, which is 11.58. Big number, which we kind of already have, but we'll go 500. And then 0, our average in our standard deviation of our normal curve. And again, you're going to get a really funny looking number. You're going to get like 2.68 e to the like negative, I think 31, which remember this is going to move that over way far. So this is essentially 0. It's really, really close. And so this is less than 5%, so we're going to reject the null. Okay, that would be my conclusion. So that's 2 sample statistics. That's an example of that. So we've done 3 things. I reviewed just one sample z-test when they're large, one sample t-test when we have a small sample, and now we just did a 2-sample test. You need to be able to do all those. We did the one last week and then these 2 this week through videos. So